All right. Different setup, so I'm hoping I'm recording. I think I am. But anyway, welcome back to another lesson. Today we're going to talk about similar polygons and triangles. And as you can tell in most things in nature, not everything's going to be congruent, right? We're going to have things that are similar, but just not quite the same. And the topic for today is what makes something similar? And then how can we use that information to find measurements of similar figures, in this case, polygons, right? So let's just jump right into it, okay? So what does similar mean? Well, I like this picture a lot, but it's pretty much like animals, okay? Both of these are giraffes. Both come from the same family here. Both have spots, both have tails, both have long necks. The only thing that's really different about them is their sizes, right? We could see that this guy's a lot larger than this guy. And that's just like polygons, okay? For instance, let's just take a piece of paper, okay? So this guy's a rectangle, this guy's a rectangle. They both have similar features, except this one's larger and this one is smaller, okay? So when you think similar, think of it in terms of just like animals in a way, okay? You have a baby, which is a mini version of the full adult, okay? Definition. Similar polygons are similar if and only if their corresponding angles are congruent and their corresponding sides are proportional. Okay, congruency is a big thing in this, right? So looking at this, if these angles were not congruent, then I'm looking at a polygon where one is going to be like this, but the other one's going to be like even more awkward, asymmetric than the original. So congruent is important. But this part's even equally important. Its sides are proportional. So what does that mean? So taking a look at both of these quadrilaterals, I can see that all of these side lengths right here were multiplied by 2, and I get these guys over here. 5 times 2 gives me 10, 2 times 2 gives me 4, 3 times 2 gives me 6, 1 times 2 gives me 2. Because all of these side lengths were multiplied by the same scale factor, this guy was proportional to it. If I were to multiply one of these sides by a scale factor other than 2, let's say I multiply this guy by 3, then this base is going to be, what, a lot longer? And then the whole entire picture is not going to look similar to this guy anymore, okay? So proportional is just talking about, did you multiply by the same scale factor for all of these guys, okay? So those are the two criteria to say that, hey, these guys are similar. Okay? Now, we have a new symbol. We no longer use congruent. We use this nice little squiggly line. Okay? So ABCD is similar to EFGH. Now, corresponding sides are proportional. So what we typically do, and if you remember from probably your middle school days or your early elementary school or late elementary school days, when you talked about proportions, you did things in terms of fraction. Same thing here. AB and EF are proportional to each other. We can write them together as a fraction. We can do the same thing for BD and FH, DC and HG, and CA and GE. Now, what this also provides us is a scale factor for these guys. If I were to divide each of these fractions, I know what the scale factor is. Now, does the order matter? Yes and no. If the larger side length is in the numerator and the smaller one's in the denominator, my scale factor is going to be bigger than 1. So I found the scale factor that I would multiply the smaller polygon by to get the bigger one. Vice versa. If I were to flip it and the small one's on top, bigger one's on the bottom of the fraction, then I found the scale factor to go from the larger to smaller guy. Okay, so the order, like I said, depending on what direction you're going in, it does matter. What would the corresponding angles be for this picture? Well, it would just be A with E, which would be 4 arcs apiece, B and F, D and H, and then C and G. There we go. Okay, so going back to example 1 here. Sorry about that. Someone just came in the room, threw my thought process off a little bit. So example 1 says just list the corresponding angles and then list the proportions for this guy. List all the sides that are proportional to each other, okay? Doing this isn't too hard of a task for us to accomplish here. Let me just see how this is going to be done. How am I going to fit everything in? Can I? I think that'll be okay if I do something like this. I think so. We're going to give it a shot. Okay. Let's look at the proportional side lengths. Okay. I only need this PowerPoint for this example, and then we're done. So taking a look, I can see that FG would be similar to JK based on its position, right? It looks like I just took this triangle, shrunk it, and I got this guy a little bit, okay? You can also look at it by its statement. See how FG is in the first two positions, JK is in the first two positions? Because of that, I could say that they're similar as well. Just kind of relating back to linear congruency. Okay, another proportion that we could set up would be GH and KL. They're both at the very bottom. And finally, we could say that FH is similar to JL. So those are all of my similarities right there. For the congruency part for angles, we know that F would go with J, G would go with K, and then H would go with L. So that's what's asking you. Can you set this up? Now, the fractions right here, you could flip them. That's fine. It's going to mean the same thing. And remember, these are telling me the scale factor as well. Okay? What do you think? So far, so good? All right. Now we're going to do a couple examples. Put all this into practice. I do not need a PowerPoint anymore. All right. Let me just adjust some things here, guys. I apologize. Let me just adjust the camera. Maybe. Okay. There. Okay. There's problem one. Oh, need a marker. I use blue, so I'm going to make sure I have a blue marker. All right. I have a similarity statement over here that I could reference to. I have these two. It looks like trapezoids without, doing any measurements to confirm that. And what I'm trying to do is figure out what X and Y are. Okay. And we could do this a number of ways. It just depends on, well, your preference. Okay. What I'm going to do is I'm going to show you how to use this with scale factors. And in the next example, I'm going to show you how to use it with proportions. Sound like a plan? And then you could choose which method you would like when completing the homework assignments. All right. So here's what I'm going to do. So using scale factors, here's like the first method that you could try out. So notice that if I look at 9 and 6, those guys would be similar. Based on just what this looks like, I took this quadrilateral, I reflected it, and I shrunk it. But if I'm not sure, look at the statement. CD is in the, almost the middle part, and then I could see that going with it would be YW, which is right here. So it looks like I'll be okay with this one. Oh, wait a minute, A, C, D, F. Oh my gosh, I put B in there. I put an extra letter without realizing it. I apologize. All right. Now, because 9 and 6 can be similar together, I can figure out the scale factor by a little bit of division, right? So 9 divided by 6, I get 1.5 for that guy, okay? Now, because this is bigger than 1, that means that if I multiply a side by it, it's going to get bigger. So if I multiply 6 by 1.5, I get 9. So there's my scale factor. If I want to go in the reverse direction, instead of multiplying, I divide, right? So if I go from 9 to 6, I divide by 1.5, and I'll get that result. Okay, so far so good. So now what I'm going to do, knowing this key piece of information, I'm going to go ahead and figure out what X is right here. So looking at this, I can see that ZY inside FD are similar to each other based on the picture, and I can tell based off the statement too, right? So FD is in the last two positions, ZY is in the last two positions. Okay. Now, if I take this guy, multiply it by my scale factor, I should get the ending result, right? So let's see. FD would be 10 times 1.5. And when I do that, I get 15. okay, which is what x is. Okay, so x comes out to be 15. Not too bad, right? Okay, now I got to figure out what y is. I'm going to do the same thing. AF and ZV are similar to each other. And I can see that here. First and last, first and last. Okay, statement confirms it. If I multiply everything here by 1.5 to get these guys, now I'm going in the reverse direction. So to go from here to here, instead of multiply, I'm going to divide by that scale factor. Okay? So what I'm going to do first is figure out what is the length of this guy. That's going to be 12 divided by 1.5. When I do that, I get 8. Now that's not the answer. That means that this entire length is 8 inches, 8 feet. I don't know what it is yet, but it's 8 something. Now what I'm going to do is I'm going to set this guy equal to 8 because this guy adds up to be 8, right? And that can help me find y. 3y minus 1 equals 8. And now I'm just going to solve it. Add 1 to the other side. I get 3y equals 9. And then divide both sides by 3. I get y to be 3. My final answer. What do you think? Not too bad, right? Now, can I check my answer? Absolutely. If I plug 3 into here, 3 times 3 is 9. 9 minus 1 is 8. We're good. Okay. What do you think? Questions, thoughts, concerns, dilemmas? That's method 1. Okay, using a scale factor to figure out the side lengths. And you just have to be careful, okay? Remember, if it's bigger than 1, then you're what? Making a side larger. So that means your smaller polygon, I'm multiplying it by that number to get this guy. Now, if I want to go the reverse direction, you would just divide, okay? And you can always confirm this by crunching the numbers up. All right, what do you think? Try something a little different. So method 2, and I'll do this with another example. There we go. Okay. See, I'm just moving you across the classroom. See, you're here. You really are here. I have these 2 triangles, and what I'm going to do is I'm going to use this by proportions. So using proportions. Okay. And this should sound a little bit familiar from your Algebra 1 days. So instead of scale factors, I mean, I could figure this out by scale factors. Let's make this clear. If JL is similar to TQ, I can tell by the congruency arcs and by the statement. To go from 2 to 4, my scale factor has to be a 2, right? So that's not a difficult thing to accomplish. But let's say I didn't want to do that. Let's say I want to use proportions. What I'm going to do is I'm going to set the sides equal to each other by similarity, okay? What do I mean by that? Well, see how 4 and 2 go together? Okay, and that gives me what? A scale factor of 2, right? Now I'm going to go ahead and write 2 other sides that go together. And it should give me a scale factor of 2, but since I don't know what it is yet, that's okay. And you'll see why. Notice how I went from large to small when I wrote this first fraction. You can go from small to large, that's okay. Just make sure you write the next couple fractions similarly. Okay, not to use that word so many times. Pick a side. Let's solve for x first. No reason why. Okay, so x is part of the larger polygon, so I'm going to put that in the numerator. And then in the denominator, I'm going to go ahead and put what side this is similar to. ML would be similar to, I believe it's going to be what? ST, right here. Be similar to 3. And I know that because of the statement, ML and ST, but I also know because of the congruency marks. See how that has 2 arcs? That has 2 arcs. Okay, it makes it easier. Now notice I set these equal to each other. They should be equal, right? If this gives me a scale factor of 2, so should this guy. As long as I know what x is. That's what I'm going to solve for. Usually what? When you see something like this, the first thing that comes to mind is, hey, cross multiplication. And absolutely, that's what it comes down to. Could you solve this without using cross multiplication? Yeah, and actually it's the same method, it's just done a little bit differently. But I'll go ahead, I'll go with the the majority here. So yeah, you're going to cross multiply these to solve it. 4 times 3 gives me 12. And then I'm going to multiply this next diagonal together. Doesn't matter which one I multiply first, by the way. And it's going to be 2 times that numerator. Now, the numerator has more than one term in it, huh? It has 2 terms. I got to be careful. That's why I wrote it this way. 2 has to get multiplied to every part that's in the numerator, okay? When I distribute, I get 12x minus 6, and then I can go ahead and solve for x. Add 6 to the other side. I get 18 equals 12x. Divide both sides by 12. And then x comes out to be 1.5. Okay. Good. Questions? Now, what does that tell me? I'm so glad you asked. If I plug 1.5 back into here, let's say I did that for a second. Okay. I'm going to rewrite it over here. 6 times 1.5 is 9. 9 minus 3 is 6. Okay, so look what happened. When I plug this back into here, I get 4 over 2 equals 6 over 3. Is that a true statement? Absolutely. 4 over 2 is 2. 6 over 3 is 2. And that's the scale factor, right? 2. That's what we talked about before we jump into this. Does that make sense? Okay. So when people see this, like, well, why you said it equal? Well, because they are equal. we're equaling the scale factors. Okay, now we're going to figure out what y is. We're going to use the same approach to it. Because 4 over 2 worked so well with the first fraction, we're going to use it for this guy too. And it makes sense, right? The scale factors too. Now, here's what I would recommend it. I would not use 6 over 3 to solve for y. Why would I do that? Well, if you get this guy wrong, then this is automatically wrong, right? 4 over 2 we know is correct because the problem tells us this. So why don't you just keep it? Now, we're going to have 3y over 2 be partnered up with what? Well, that's what? Jm. So qt would be the other guy, which would be 2. Okay? Or, there's an or here. Or you could take a look, and actually, oh, not 2. I apologize. It's a 5. If you take a look, oh, wait a minute. Did I do this right? JLMQST. JL goes with, that's an L, that's an M. I copied it wrong off my notes. I apologize for that. If you guys were screaming at the computer, hey, you made a mistake, I caught it. See, I was listening. I heard you. Okay, so I'm sorry. JL would go with QS, which would be over here. Okay, so that works by the statement. And now what we're going to do is cross multiply to finish. So we're going to multiply these guys together. And I'm writing it out fully so that way we understand what's happening. And then we're going to multiply these two guys together, and I'm getting 20 for that. Multiply 2 through everything. 6y minus 4 equals 20. Okay. Add 4 to the other side. I get 6y equals 24. And then for my last step, when I divide by 6, I get 4 as my answer. Does that work? That's what you should always be asking yourself, and it should. If I plug 4 into here, I get 3 times 4, which is 12. 12 minus 2 is 10. I already know the scale factors too because these two sides help me figure that out. So 5 times 2, does that give me 10? It does. If I plug 1.5 into here, I got what, a 9? Or not a 9. I got a 6. 3 times 2 gives me 6? It does. Okay? So in other words, we're good. Everything checks out. Looking at both of these methods, okay, whether it's by proportion or just using the scale factor, it's up to you. It really is. You're going to get the same answer no matter what. What comes easier to you? All right. I will say using scale factors might be more hands-on, might be, what's the word I'm saying? Easier to comprehend. Setting up a proportion, it just depends. Okay. But I wanted to give you both of these examples. I did 2 different methods. You get to choose which one you'd like, okay? And just to final things up, remember, to be similar, the angles have to be congruent and all the sides are proportional, meaning that all the sides will multiply by the same scale factor, okay? That's it, guys. That's part 1 of this lesson. Part 2 will come later on this week, where we start talking about triangles and how do triangles fit into this. I know that sounds weird. How do triangles fit similarity with just a couple parts? No, it's kind of like congruency in a way. So anyway, hope you have a good day. I'll see you all in the next lesson video.